So we're going to start with first order optimization algorithms. So again, the most common and the most widely used and best known example of a first order optimization algorithm is gradient descent. We're going to talk about a bunch of different flavors of gradient descent. But any gradient descent based algorithm looks something like this. We start with some specific value of our parameters that we might call theta 0. Again, notice the boldness, the bold notation, so this is a vector of parameters. We're not going to talk too much in this course about how to choose a initial value for our parameters, although that's kind of an interesting topic in its own right. But we start with some initial values for our parameters, and then we iterate this update, theta t plus 1 equals theta t plus the following, some scalar value that we've written here as nu t times dt, which is our descent direction. This we often use the derivative of our log likelihood function with respect to theta. By the way, let's look at the notation that the textbook uses. So first thing, we're using the capital delta sign to indicate the derivative. So we use this when we're indicating the multivariate derivative versus the d over d theta that we would use for a univariate derivative. And so we have the derivative of L theta, our log likelihood function. We're going to specify that it's the derivative with respect to theta, and then we're also going to specify that we want the derivative at the specific value theta t. So this is what we'd often use for our gradient descent. We'll talk about a couple of reasons why we might not want to use exactly that. We might want to use something close to it. We can also write it in univariate form. It's this vector here where dt equals the vector of partial derivatives as follows. The first is the partial derivative with respect to theta 1, with respect to theta 2, and so on. So again, there's two things we need to think about here. One is the thing we just talked about, our descent direction d, which we usually take to be the derivative of our log likelihood function. And then the other thing is our step size. The simplest thing to use for our step size is just some constant value that would be a hyperparameter to our function. I'll talk a little bit in a minute about why we might want or not want to use a constant value. So all of our first order optimization algorithms take this form. So again, we're going to talk about a couple of different flavors of gradient descent algorithms that depend on different choices of our step size and our descent direction. Let's start with the simplest option, which is to use a constant step size. So constant step size is very often used in practice and often works okay, but there are some issues. So we're going to talk on the next slide about the cases where a constant step size might not converge. That is the case where you just go back and forth and never settle on a global optimum, or sorry, even a local optimum. But it's worth noting that it's a bit of a misconception that the constant step size doesn't always have this issue. That is, in many cases, using a constant step size does converge. So I think the reason for this misconception is, let's imagine we're doing our optimization here, and we end up at this point, and we might think that a constant step size means we go a constant distance in parameter space. And it's easy to see that if every iteration we go a constant distance of the parameter, then we're never going to converge. We're just going to jump back and forth across this local optimum. But don't forget that we're multiplying this step size by the gradient, and that is both the direction of the gradient as well as its magnitude. So in this simple example, if we started here, for example, we would take a big step here from the place where the gradient is steep, and once we get here to a place where the gradient is shallow, we'll start taking shorter steps. And it's very possible that we end up converging very close to this optimum here. Now that said, we're not guaranteed to converge using a constant step size. And in particular, if the step size is too large, it's very possible that we might never converge. So let's use this as an example. So we're using this function here at the bottom. We're imagining that we're trying to optimize this. And notice that there's nothing too crazy going on here. This is just a polynomial. By the way, this is a function of two variables, theta1 and theta2. And notice it's just a polynomial in those two variables, with the highest order term being theta1 to the fourth because of the squared here. So the function looks like this. By the way, the function is convex. So if we start here and we iterate using a large step size, the optimization turns out to do this. It's jumping back and forth, never reaching the optimum. So this is a problem with that can occur when using a constant step size. The flip side, if the step size is too small, is you can take many, many iterations to converge. So here on the left is the case of using a small step size, and you can see that we're running many, many iterations. And in fact, as we approach this area where the derivative is shallow, that is, our objective is pretty flat, we end up taking many, many iterations to go even a small distance. So given issues with using a constant step size, let's look at a couple of other options. The first is line search. So at each iteration, again, we compute this descent direction d. So another option is to ask, maybe let's just say, let's try to find whatever value of the step size that minimizes this function, now having chosen a specific descent direction. So that looks something like this. Let's imagine we have the following function. I'm drawing it in the level set form. So this is a 2D function, and I'm drawing the level sets of our gradient function. So first we compute, and so here's our current value of our parameter. We compute the derivative. We see that it's in this direction. We say, okay, let's figure out what value along this line minimizes the function. So that gives us the following kind of mini optimization algorithm. Notice that where we started with a multivariate optimization algorithm, where we're trying to optimize all of the values of theta t, in this case, this is just univariate optimization, because all we're trying to find is a value of the step size nu. Now, in a lot of cases, it's actually possible to do this univariate optimization analytically. That is, you might not be able to find an analytical solution to your whole optimization algorithm, or for your whole log likelihood, but sometimes if you restrict it to this univariate case, you can actually analytically find the solution. That is, you just write out what this is. You take its derivative and set it to 0, and sometimes once you do the algebra, you can find that solution. Another option is to do what's called backtracking search. That is where we first pick some constant initial step size. Let's say that takes us all the way to here. And then we ask, at that new location, we compute the new likelihood. And if we find out that it's worse, or in fact even not sufficiently better than our current value, we'll backtrack. That is, we'll pick some smaller value of new, and we keep doing that until we find a value that's sufficiently small. And then we call that our new value of our parameters. So those two, the analytical solution and the backtracking line search, those are two examples of line search for gradient descent. Let's look at another alternative to using a constant step size, and that is the following. So here we're defining our update like this. Our new parameters equal our old parameters plus the following. This is a different descent direction, and in particular it's the following, which is we take our old gradient that we've seen before, our step size, times our gradient, plus beta, which is a hyperparameter, times the descent direction we used at the last step. And beta is going to be a small value between value between 0 and 1. So the advantage of this is that notice that in the case where we go in the same direction in the previous iteration, we go the magnitude of our update is going to be larger than it was than it would be otherwise, because we have the contribution of both the last iteration and the current iteration, both pushing us in the same direction. But in the case where the gradient has switched directions, that is, we're going in the opposite direction that we did in the previous iteration, this is going to be smaller, even 0. So the advantage of this is that we're going to speed up, and in fact, because we keep adding in the direction from the last iteration, notice that we're adding in this. Notice that we're not just adding in the gradient; we're adding in this whole descent direction from the last iteration. So if we, and this one is defined, based on the one before it and so on. So in the case where the gradient is the same many iterations in a row, we're going to end up with a very large magnitude step size here. And notice that the magnitude is going to be different per parameter. So this is a vector, and we're doing this, of course, vector addition. So for parameters where our derivative is the same, that has the same sign from iteration to iteration, we're going to end up going faster, and we're going to end up slowing down in cases where our gradient switches from iteration to iteration. So this is specifically aiming to address the issue that we saw in the first example, that gradient search tends to go very slowly in cases where the derivative gets very flat. And momentum has the effect of accelerating us across very flat parts of kind of the likelihood landscape. So this method of momentum is quite effective, and it's used very often in practice. So So those are a couple of different flavors of gradient descent: the fixed step size, the line search, and the momentum.